All right, everybody. Good evening. Welcome to the Virtual Science Cafe. I am your host, Chris Smith, curator of the SCCU Daily Planet Theater, here at the wonderful and inspiring North Carolina Museum of Natural Sciences. Thanks so much for joining us. Thanks for tuning in. If you are a regular visitor to our Science Cafe virtual series that we've been doing since April, then you might notice that my surroundings are a little bit different. And if you've ever joined us in person at the Science Cafe, you might recognize the scenery a little bit. We are here inside the Daily Planet Cafe at the museum in downtown Raleigh tonight. There's nobody here except for me as the host, our very special guest, and our digital media technician who's up on the second floor of the museum to bring you the program tonight. We needed some super duper internet connectivity, some like Star Trek Enterprise level stuff in order to bring you the program tonight, because we've got some amazing visualizations. We're going to be using this incredible software called OpenSpace to visualize the universe and see what's going on, all based on real data. You're going to learn a whole lot more about that in a little bit from our special guest. But I just think it's incredible. It's very surreal to be back in the museum, even just for this like one night to do this one show and to be talking to an empty cafe. Anyway, I think it's pretty wild. Let me bring on tonight's special guest. Dr. Rachel Smith is the head of the Astronomy and Astrophysics Research Lab here at the museum and a professor at Appalachian State University. Rachel, welcome to the show.
Thank you, Chris. Thanks, everyone. You've been a great audience so far. So
I'm sure if there were people here, they would be clapping and cheering and so excited to learn about space.
Excited. Well, space is exciting, and I'm really excited to show you what we're programmed today about asteroids and comets and planets. And so just let me know when we can get started. And we're going to use software called OpenSpace, as you said, which is a NASA-funded project that's led by the American Museum of Natural History. And everything that you see is real data. So that's what's really cool about it. We're going to drive around space a little bit. We're going to go to a few key locations on Earth, go to asteroids and comets and talk about those, and then end up on Mars. We're going to land on Mars and stay there. That's the end of the program. So,
well, I'm excited to do our little flight through the universe here.
Yep.
And hear the stories that you've got to share. I do want to remind everybody watching online, wherever you happen to be, whether you're watching on YouTube or other social media sites, use the chat box and the comments threads to leave questions as we go through the program. I'm going to be monitoring all of the comments right here, so you can leave your thoughts, your questions, and when we get to the end of the OpenSpace program, I'm going to grab your questions and throw them to Rachel, 8 feet away from me on the other side of the stage, very safe distance away from us. And we both have masks here in case we need to step off the stage for any reason. We're ready to go. Anyway, keep up the conversation. Let us know what you're thinking in the chat as we go along, and I'll be keeping an eye on that.
all right.
Rachel, let's get started.
As soon as we share, are we ready to share content?
Go for it.
Oh, okay. So I don't see it. You don't see it.
There it is.
Oh, there it is. Okay, Earth. All right, so this is our home. This is Earth. And what I'm going to show you is what you're going to see is a menu popping up. And this is, if you download OpenSpace yourself, if you feel like trying it out, it's openspaceproject.com, and you'll see these menus. And I have some bookmarks set up for this program. And we're going to talk about basically impacts on planets and why those happen, where they come from, impacts from space. And we're going to start with something that may be familiar, a location that may be familiar to some people. This is Earth. And again, this is this Fly Through the Universe software, which is really cool. So we're going to drive now to Meteor Crater, which is in Arizona. And I just put a little marker on it here. And so when rocks hit planets, they often leave craters. And this happens all the time, and we're going to talk a little bit about that. Let's actually go make sure we get here first. Sorry, getting a little bit excited about it, so I turned it off. There it is. So Meteor Crater is one of the best preserved craters on Earth. These gray tiles are just data loading, so don't, this is actually pretty awesome data, pretty high resolution. You almost feel like you're there, except for these gray tiles, which will come through or not. Meteor Crater was an impact that happened about 50,000 years ago. So this is in Arizona, near the Grand Canyon, and 50,000 years ago, it was cooler and wetter in this region of Arizona, so it wasn't as hot and dry back then. And what sort of creatures might have been around 50,000 years ago? Well, we'd have giant sloths like this cutie here, and woolly mammoths as two examples of animals. Now, this crater is not that big for a crater. It's very well preserved. This building here is a visitor center, so it's one of the most well-visited craters on Earth. There are about only 128 craters on our planet that have been preserved that we know of, and that's just a tiny, tiny fraction of what's hit our planet. But the impact of this size, about maybe a few tens of kilometers or so, wouldn't have caused extinctions, wouldn't have caused vast devastation, but certainly it would have been felt by whoever was around at the time. But it wouldn't have been as devastating as some other impacts that you might know of, and we'll go to one of those. One location that may be a little bit more familiar. We'll zoom out a bit and go over to a crater called Chicxulub. This is in the Yucatan Peninsula, which is a part of Mexico. And we're just going to spin this around a little bit to get a look. Now, as many of you know, most of Earth is covered in water. And actually, what I'm going to do here is I'm going to make it a little brighter. There we go. We'll wake up these regions. You can change time with OpenSpace. You can have fun with data sets. So that's one of the great fun things about OpenSpace is you can turn data sets on and off. You can make it day or night, whatever you like. So let me turn this little sphere off. Now, so this is a region where the crater was actually discovered here, right around, it's underwater, so it's not visible to the eye the way Meteor Crater is. But what happened here is it was discovered underwater. It's been confirmed that 65 million years ago, this impact happened, and this is about what it looks like, the region. This is in Spanish. This was the best image I could find was in Spanish, so some Spanish scientists made this. This is the center of the crater, and what happens with impacts is you get what's called an ejecta blanket, and that would extend right about to here. So they've discovered, they did chemical analyses and all sorts of interesting geological analysis to know that 65 million years ago, this impact happened. And what happened 65 million years ago? If you were here, you'd probably shout out. It was the extinction of the dinosaurs. This led to the demise of the dinosaurs, which actually, we think of impacts as being devastating, and we're going to talk about, this looks like kind of a bad day for these flying reptiles, but it did open up environmental niches for mammals and are the precursors to humans at some point. We evolved much later in time than this moment here, but it did open the way for other species such as humans. And so that is, we probably like that idea. So Chicxulub, so if you ever get a chance to visit this region, you'll know that this is the region of the dinosaurs. So, of the dinosaur extinction. So we think about, you might think, well, these impacts are terrible. How often do they happen? Do we have to worry about that? And the answer is not so much. So an extinction, this is a plot that shows the typical time between impacts on this axis and the size of the impactor. And this impact here, this called the KT meteor for when it happened, this would happen every 100 million years. And this is, so we think 65 million years ago, that's not so far away from 100 million years. Well, maybe we're due for a big, massive impact, but we wouldn't worry about it right now because there isn't any asteroid that we know of this size that we can detect that could cause this devastation. But you'll see the bigger the impactor, the planet-wide destruction here would only happen once in a planet's history, really. And so these are very rare. What's not rare are small little impactors, and we get these every day. We get hundreds of tons of dust particles coming to Earth every day. And most of these burn up in the atmosphere. And one famous one, which actually wasn't very large, this is only 10 meters in size right here, exploded over Russia in 2013. And it came in as a fireball, and it looked like this. And this is from a screen cam, a dash cam, sorry, on a car. I think we've been on the computer so long I haven't been driving, so everything's a webcam. But this is a dash cam in Russia, in Chelyabinsk, in the city of Chelyabinsk, and this is what it looked like. We do not have detection mechanisms to detect small impactors like this. This was only a 10-kilometer or 20-kilometer asteroid, a meteor that exploded in the atmosphere. So this could not have been predicted. It came through, it burns through the atmosphere, and what it looks like when it burns is a little piece that I was able to buy in Chelyabinsk a few years ago when we were in Russia, is it looks like a charred surface because it burns up, and you get this bright meteor that comes through, and the material that you pick up are called meteorites. And so these meteorites come from the asteroid belt, which we're going to fly to in a minute. And so the asteroid belt is full of, there are billions or millions of asteroids and billions of comets, and these are the leftovers of the solar system's formation 4.5 billion years ago, roughly. And so these little pieces that come to Earth, and from what we can study using telescopes and sample return missions to asteroids, is we can study the early solar system with little pieces like this that come to Earth. And so these impacts are really interesting scientifically to understand the early solar system. Okay, so this is Chelyabinsk. So one other interesting thing we're doing at the museum with this meteorite is we're able to scan it, to use a CT scanner and look inside the meteorite without destroying it. And what we see, I'll just show this little image. This is a scan showing density, and what you can, the white is metal, and these other colors are different densities of stone. And the blue outline here is that charred surface. So it really shows up in different color palettes you can pick with the code that we use. And so this is one way we can study this meteorite, and you can see these cracks. This asteroid, before it hit, was knocked around in space for millions of years, and it's a very interesting sample, and so we're studying that now. Okay, so let's zoom out a little bit, and we looked at a little piece of an asteroid there, and the last place we'll stop on Earth, we're going to go to one more stop, and that is a lake, and that is a different kind of crater. This is Lake Salda, and this is going to try to remember this lake for when we go to Mars. This is the lake, this is the only lake known where there are these carbonate sediments. This is in Turkey, and there are these carbonate sediments that make it the exact analog to where Mars 2020 is going to land in 2021. It took off, it launched last week, if I remember correctly. We're going to make it light and wake up Turkey. There we go. All right, so we'll zoom in here. Right. And you can see here's the lake, and it's a very unusual lake. It's actually a recreational area in Turkey. You'll see this, this white outline. These are carbonates, and there's also magnesium in this lake, and there's very interesting mineralogy and geology around this lake. This has been studied extensively to better understand what could be happening on Jezero crater, which is on Mars, which is our last stop. There's a delta here, which is very similar in formation. It's similar to how Jezero looks, and we're going to look at that. And so when we think about Mars, Mars is a barren landscape. It looks barren now, but millions of years ago, billions of years ago, maybe not so long ago, there was water, very likely water on Mars. And it's thought that Jezero crater was filled in, just like this, was a flooded crater. There is evidence of carbonates in that crater that scientists know about from spectroscopy of an orbiter on Mars. And so studying this lake and understanding, how life could have started on Earth and how life might have started on Mars is really critical to these missions and where we should send them. And so this is our last stop. This is a crater, but it's actually a caldera, so it's formed from volcanoes, a volcanic crater, and then filled in with water. And so you get craters from impacts and craters from volcanoes. Jezero is a double impact crater, and we'll look at that. It's pretty cool. So these impactors, these asteroids and comets that hit planets, they create these regions where water can exist, and then maybe life can evolve in those and possibly start in a region just like this. Okay, so we're going to now zoom all the way out, leave Earth. We're leaving Earth, and we're going to take a little journey to the asteroid belt and the comets, and we're going to take a look at the solar system. Actually, we'll turn off Lake Salda, and we'll turn on some trails and labels. There we go. And let's focus on the sun, our star. All right. Okay, so these are our planets. We have 8 planets. You will see a label for Pluto. Pluto is not a planet, and actually we'll learn a little bit why in this program. But we'll take a look. These are the orbits of the planets in our solar system. Our solar system formed about 4.5 billion years ago, and the remnants of that formation from a disk of gas and dust and rocks are the asteroids and the comets. And so let's turn on some comets. This is Neptune here. You see Neptune in blue, and Pluto's this little rock out here. It looks like it's lonely and sad it's not a planet, but it actually has a lot of neighbors. And the discovery of these neighbors, in OpenSpace it's called the trans-Neptunian asteroids. They're actually more like comets. They're these. So Pluto, if you look closely, Pluto right here with this little label has millions of neighbors. And so Pluto really shares a lot of characteristics with these objects, these icy, rocky objects in the outer solar system, or beyond the orbit of Neptune right here. And so this is one of the discovery in the 1990s of this Kuiper belt is one of the reasons why Pluto is not a planet. It's only one of the reasons. Some of these orbits that you'll see here, this is a database, by the way. What you're going to see today, when all of the data points that you see, these trails, there's about 900 and nearly 940,000 data points that have been input in OpenSpace, which got me really excited to do this program, because now we can talk about asteroids and comets and meteorites. So here's one set of comets. So these are the trans-Neptunians. So there's Neptune here, and we'll turn on some other families of comets. Now, we know about comets because they sometimes come close to the sun, and they come near to Earth, and that's when we see these beautiful images of the comet. Most of the comets that we see are short period comets that come around roughly every 50 or to 150 years, and they come from the Kuiper belt. But some comets, very rarely will see a long period comet. When that originates in a cloud of what scientists think are billions of comets, thousands and millions of miles beyond where we are now, which we won't go to there. That's called the Oort cloud. And so that's a long period comet. And some of you may have been fortunate to see the long period comet that came, that was around in July, and that was Comet Neowise. And this is a picture I was able to take outside our house in Cedar Grove, which is near Hillsboro, and there's the comet right there. And so it's a long period comet. It won't come back for another 6,500 years, and it's just really cool to see a comet in your night sky if you're able to see it. But comets do come around, and they deliver stuff to Earth, and we'll talk a little bit about that. So there you have some Chiron type, Encke type, Halley type. Halley's comet is one of those, an orbital period about every 75 years. And then there's the Jupiter family comets, these little green. Let's turn off the trans-Neptunians so you can see these. So Jupiter, we may not think about Jupiter very often. There's Jupiter, but here are a few of the Jupiter family comets. They have an orbital period of less than 20 years, and they're very interesting. One comet in particular, a Jupiter family comet, which comes around fairly frequently, is 103 P Hartley 2, and that is this comet. This was discovered several decades ago, and what's particularly interesting about this Jupiter family comet is what you see blowing off of it here is the water coming off. It goes from ice to gas as it nears the sun, and that's where you see that really beautiful tail. And with Comet 103 P Hartley 2, they actually were able to analyze the water in this comet. And this is the last plot, I promise, that I'm going to show. But what I love about this plot is it shows a spike here. And this spike is a type of water. It's a heavy water. And this water, what they looked at is look at different types of water in this comet. And they compared that water to our oceans. And it turns out that the ratio of heavy hydrogen, which is this D, to normal hydrogen here, is the same as on Earth. And this was evidence, or it's supportive evidence that water could have been delivered to Earth by comets in the distant past. And so we don't know how Earth got its oceans. 75% of the Earth is covered in water, and so it could have come from comets. And this is one comet which shares a similarity in chemistry of water. So that makes it pretty exciting. So let's just consider Jupiter for a second, and we'll turn off these comets for a minute and just go to Jupiter, and then we'll go take a quick trip to the asteroids, which are closer. And so here we're going to go to Jupiter. Jupiter is our largest planet by far. In fact, it almost was a star. It failed to become a star, but it's a pretty awesome planet. For when we think of the origin of life on planets, and I'm going to turn off shading here. We don't need to see nighttime. So it's going to be light on Jupiter. Here's Jupiter. There's a mission on Jupiter now looking at the atmosphere, Juno. And Jupiter is very famous for its red spot, which is a storm. Here, an enormous storm, many, many times the diameter of our planet. Jupiter has been called a cosmic vacuum cleaner. It's been said it mops up asteroids and comets, so it mops and it vacuums. It's just a great planet. And what Jupiter does is it protects the Earth from a lot of impacts. And over the evolution of Earth, it likely protected Earth from a lot of devastating impacts. And Jupiter is hit thousands of times more frequently than all other planets because it's so big and has such a strong gravity. And one really famous hit of Jupiter, the only time that an impact has been seen on another planet, is, well, I'll get back to that one, is Comet Shoemaker-Levy. Comet Shoemaker-Levy was a comet that was discovered by the wife of Eugene Shoemaker, Carolyn Shoemaker, and it was discovered in the 1990s. And as it came, it was a comet that was captured by Jupiter. And as it came close to Jupiter, it was pulled apart by Jupiter's gravity. And what's called here a string, they called it a string of pearls because it was pulled apart by Jupiter's gravity. And then it smashed into the atmosphere of Jupiter. And this is an image taken by the Hubble Space Telescope, I think, that shows these impacts on Jupiter that were observed. And so it was very exciting, and it was clear that Jupiter is hit. We kind of assumed it was, but this was clear evidence in real time that Jupiter was hit. And the scars of this impact were below the red spot, as big as black scars that look kind of similar. They scarred the atmosphere for many months when they released all of the gases into the atmosphere. Jupiter is a gas giant, so it has no surface, but it still gets a lot of impact, and it can hold a lot of gas because of its mass. Okay, so thanks to Jupiter for our existence, truly. And so let's zoom out a little bit again, and we will turn on the asteroids. Now, most of the meteorites, as I said, they come from the asteroid belt. Asteroid belt is much closer. Let's go to, here we go. Let's go back to Earth. And there's Earth being covered by asteroids here. So we're going to look at, again, most of what I show you here are going to be asteroids, most of the data points. And so these are, the ones I'm turning on here are Apollo and Aten asteroids, Atira. These are all pretty close to Earth. Most of these won't impact Earth, given our understanding of their orbit now. But we have outer main belt asteroids, inner main belt asteroids, and all of these asteroids, and we have potentially hazardous asteroids, which we'll look at in a second. But this is, you can just see there are millions. This is only 1 million or a little bit less asteroids. These are a few thousand, just an example of some of the data. It's not even all of the asteroids. And you may think, well, wow, we should be hit all the time. But the thing to remember is that asteroids are not only millions of miles from Earth, even the ones that have a close path to Earth, but they're also millions of miles away from each other. And so when you see in science fiction films, like in Star Wars, there Empire Strikes Back, they show being, almost the spaceship almost being hit by asteroids. That's definitely artistic license, because they are so far apart that would never happen here. Of course, that's in a galaxy far, far away, so who knows about their asteroid belt, but it's kind of unlikely. Okay, so one thing to think about, we think about asteroids, and I actually skipped that picture, but I'll go back to it, is we think about what could we, sometimes it comes up, sometimes you hear in the news maybe about asteroid mining. Could we go to an asteroid and get some really interesting, maybe we need some minerals or water eventually on Earth. And there's a lot of talk about that. We've gone to the moon, certainly. We've brought back many, hundreds of tons of rocks from the moon. And asteroids they have cobalt, they have ore, they have gold. They have lots of elements that we actually don't have a lot of on Earth. And there is talk. This is actually a rendering from NASA with a futuristic interpretation of what a mining operation could look like on an asteroid. Now, we aren't at this point in technology of having, your whatever this thing would be, a tractor of some sort, your asteroid tractor, and this kind of apparatus. But it may not be so far in the future. If we get to the moon again and set up some kind of regular transport to space, which it's looking like we might be able to do with SpaceX now really in the game, that maybe this would be possible in the future. Okay, so one thing, so it's fun to fly around. I'm going to turn on the main asteroid belt, and then we're not going to drive around that because it's actually it's very large, and it's hard to navigate because of the size of it. But what you're seeing here, these are like 80,000 data points. Sorry, 80,000 data points. This is the main asteroid belt. So most of the asteroids are in this belt. They're usually in stable orbits, though stuff gets knocked around sometimes, and then we certainly can get meteorites from the main asteroid belt. And one meteorite that's really cool, I think, and so I will share with you, is originates from a particular asteroid. This is the trail of that asteroid. It's in the main asteroid belt. It's called Vesta. And to go there, we're going to turn off the main asteroid belt and turn on Vesta and go to Vesta. So there's a little model in this in our latest version of OpenSpace, which is fun to see. So we'll just zoom over there. Takes a second. A lot faster in OpenSpace than it'd take to fly, for sure. So here's our asteroid Vesta. And this asteroid, you can see craters. Certainly, Earth has 128 craters. That is a tiny fraction. Earth is always regenerating the surface. It's 75% water, so most of the hits are in water. But that's not true for other planets. So you'll see there are about 300,000 craters on Mars and millions on the moon. And all of these little asteroids certainly preserve crater hits from billions of years ago, even from when they were formed. So what's cool about Vesta? Well, the interesting thing about Vesta, we've gone to Vesta with a spacecraft Dawn and taken imagery of Vesta. It's one of the largest asteroids. But there is one meteorite that comes from Vesta, and that is Milbalili. And so this is a scan, another of those CT scans that I'll show you from our project here. And this is a kind of a more evolved asteroid. This is called a eucrite, the meteorite, and we can learn a lot about its composition. This has been studied in the literature, but we are scanning and trying to understand our sample. You can see cracks in it. Often these cracks are either from water flow or from being hit and smashed off of the asteroid. What's interesting about Milbalili is that it's the only meteorite from the asteroid belt where we know exactly which asteroid it's from. And we know that because we've done a lot of spectroscopy on Vesta and studies of Vesta. It's very large, and it's been studied. And so most of the meteorites we get are just asteroidal, and we can't tell you which one it's from. But Milbalili, we know which one it's from, and that makes it particularly interesting as well. We get some meteorites from the moon, and we get some meteorites from Mars. But everything else is just asteroidal, or it's Vesta, and it's a fairly unusual meteorite. Okay. So that is Vesta, and what else was I, oh yes, so, oh, right. So anyway, so we lost my place. Oh yes, the hazardous. Sorry, I get caught up. I get very excited about Vesta, so I lost my. So let's go back to Earth, as we're here in the asteroid belt. Here's our Earth, and we'll zoom into Earth. I'm going to turn off the labels, and let's just think for a second. I'll also turn off the trails. Don't worry, Earth's still there. Turn off Earth. No. Okay, so here comes Earth. And I'm actually going to increase its size a bit, and you'll see why in a second. All right. Oh. There we go. I'm going to make it really big, and then I'm going to zoom out a little bit more. And I'm going to turn on, sorry, sometimes you have to navigate here, the potentially hazardous asteroids. Okay, so here we go, and I'm going to turn off Vesta. Okay, so these are the potentially hazardous asteroids. Took me a second to get there. And there are several, but the thing to remember, and what we're going to do here while we just discuss them for a second, we'll zoom out a little more, is let's change our time. You can do this in OpenSpace too. You can get a little bit more. Let's do a couple, do maybe almost 5 days a second. So you see this is about 5 days every second. So that's why Earth is spinning like that. And you can get a sense of how these are flying around. These are potentially hazardous asteroids. What does that mean? It means they have the potential to hit Earth. They are about half the distance from themselves to Earth as we are to the sun. So they're fairly close. But again, they are still millions of miles from Earth. And even the asteroid in April that came, it was called a close pass, that was a few million miles from Earth as well. And so they're millions of miles from each other, which you don't really get a sense of that when you are out in space. But most of space, just remember, is space. And that's why it takes so long to get everywhere. And it actually is pretty rare to be hit by a very large impactor. It does happen, though, and we certainly have. We've seen some evidence for that on Earth. We know it happens on other planets, and this is where these impactors come from the hazardous asteroids for that planet, from our asteroid belt, and these are the remnants of our solar system's formation. So all the material that forms the planet, that formed our planet, and formed the other planets, came from the same material that forms these asteroids. And so these are the leftovers. And that's what makes them really cool, is we can learn a lot from them. So we'll go back to real time. And the last thing I'll just mention is that when we think about impacting, and we think about, you get craters, you get certainly it's a massive explosion. When an impact happens, like in Chelyabinsk, it seems like a bomb is going off. The people in the city didn't know. They thought it was a terrorist attack at first. It certainly resembled that, and there's lots of footage of this. It's a very scary thing. So there's no one interesting aspect of this to know is that we can't even replicate the damage with our explosives as what space can deliver. So that means any impactor, even Chelyabinsk, when it exploded high up in the atmosphere, it was many, many times, hundreds of times more powerful than the bomb over Hiroshima. It just happened to explode very high up. And so these explosions that happen from impactors are really devastating to planets. However, again, they deliver water. And the last meteorite that I'll mention is this one called Murchison. This is a meteorite that was discovered in the 1960s, in the mid-1960s. This meteorite is really, really interesting. It's very old. It's one of the oldest meteorites. It's an old stony meteorite. But what makes Murchison particularly interesting is that it has amino acids in it. And they aren't life, but they certainly are important for life, and they're complex organic compounds. And so we know that these can survive in space. Some of these amino acids are just like we have on Earth, and some are really extraterrestrial. And so scientists are still studying Murchison. But one thing to consider is that asteroids and comets potentially could deliver the ingredients for life onto planets. And so we're still trying to understand how life arose. How do we get our water all life needs water. All life needs organic compounds. Could these have all come from our neighbors in space, from these rocks in space? Okay, so the last stop, so I just wanted to mention that. So impacts can be very good to planets. So the last place, as I mentioned earlier, is Mars. And so let's go to Mars. Mars, where did you go? Here you are. And actually, why don't we go to our bookmark there. Let's go right to the crater on Mars. So we're headed to Mars again. We have several rovers on Mars as we go there. We just launched Mars 2020. This is going to have the rover, it has the rover Perseverance, and it will have the first extraterrestrial, oops, am I going? Yes, I should be going. There we go. Mars is far. You get impatient with OpenSpace. You want to get there. Just think if you were an astronaut, it would take you at least 8 months to get there. So, oops, I did not mean to do that. I meant to go back to Mars. Okay, let's go back. See, you get, all right. I think oh, there we go. There it went. You can always get it back. That's the beauty of OpenSpace and your computer. Unlike if I was driving, you maybe don't want me driving the spaceship because I just flew us back to Earth. But, oh, darn it. I keep doing that. I meant to. There we go. I was just going to make it a little brighter. So this is the region of Jezero crater, this little blue dot that I put in. And I'm going to turn on one data set. Remember, I told you that you can turn data sets on and off with OpenSpace. And one data set that's particularly interesting is a data set that that shows the elevation. And this is pseudo color here. It just takes a second to load. There it goes. So what you see here, and let's spin it around a little bit. So this blue area, this blue is low elevation. So this is a giant impact crater. This whole Isidis Basin is a giant impact crater on Mars. You can see how big it is. It covers almost, it's like a third of the diameter of Mars. And Jezero, which is right here, is another impact crater. So it's basically a crater in a crater. And remember that when we looked at Lake Saldo, which is just one example of a crater holding water, Jezero certainly had water in the past. And so let's zoom down. I'm going to actually turn off this data set so we can look at the real color. So these patches that you see, all of the data that I show you, this is from the Mars Reconnaissance Orbiter. This is on Mars. It's orbiting Mars now. And this circle here is the landing site for the next, for Mars 2020. And so we'll let the data load a second. This is, these patches here are very high resolution data from the Mars Reconnaissance Orbiter. So what you see with OpenSpace is really how scientists see planets. It's not necessarily perfect and polished. You get patches of data, and you can see the quality in these strips of very high resolution data. And what's starting to come in here is this delta. So this is where water fanned out as it was flowing into the crater, and you can see these channels. Jezero, this is a landing ellipse. So they give themselves, NASA will give themselves a range of landing area, but really they hope to land in this nice smooth region so as not to damage you don't want to damage your craft. But they hope to land right here. There's a shoreline. So right here, remember I said there were carbonates in Lake Saldo, where there's carbonates here, and there's a whole shoreline here, an ancient shoreline where carbonates could have been deposited by microbes. There's evidence that there's carbonates there, and whether they're microbial or not is unknown, but that's really what they're trying to understand. Another interesting thing about this mission that's going to land right here and right at the edge of this really beautiful fan delta is that they're going to collect samples and cache them for later sample returns. So they're going to collect samples from around the shoreline here, and they're going to put them in a safe place, and then for a future mission, they'll bring them back to Earth, they hope. But you can see with the beautiful data here that you can see this shoreline, and NASA's gotten really amazingly good at landing exactly where they want to go. And you can see, too, this river channel, and you can even fly down the river channel. Let's see, you'll go here. Here's that river channel. So you can see the water would have flowed this way, fanned out into Jezero crater, which is right here, this edge of this crater. So why do we care about carbonates so much? Well, we think that the first life on Earth was microbial, and there are these carbonate mats on Earth that are microbial, and not just at Jezero, but other types of mats that are similar to the ones at Jezero. And one really interesting one to think about, and I'll just show you this last image, are the stromatolites. And so this is a type of microbial mat similar to what could have existed at Jezero, where there are these layers of deposits from from microbes. And so maybe Jezero was filled with water like this, and this is thought, stromatolites are thought to have been some of the earliest life, deposited by some of the earliest microbial life, similar to cyanobacteria, other single-celled organisms. And so it's possible that billions of years ago, or maybe even a few 100 million years ago, we don't really know, Mars had water and possibly had deposits like this. So this is from Earth, by the way, not Mars. But it's thought maybe we can go back in time with this mission and find evidence for ancient life on Mars by going to Jezero. So that's the last, I'll say this is our final impact crater here and our landing site, and very exciting for understanding life beyond the solar system. So I'll stop and take questions.
Thank you very much.
Thank you.
Everybody drop clapping hands emojis into the chat box for Dr. Smith. Excellent driving, by the way.
Thank you.
Flying us through I thought you did fantastic.
Thank you.
Overshooting Mars once, I think, is fine for a novice
That was mostly the fingers.
pilot.
It's like you got the mouse. It's like driving a stick shift. I always compare OpenSpace to except I don't have anything for my feet yet. They're working on that.
So you'll have foot pedals.
Yeah, I think I'm going to recommend foot pedals.
I think you should. The folks from OpenSpace are watching, so OpenSpace, there you go. There's your next development for how to drive OpenSpace. So yeah, I'll remind everybody, use the chat and comment boxes to leave your thoughts and questions, and we'll get to those in just a moment. There's already some great questions lined up in here, and some ones that are great but maybe off topic. I'm not sure. Thanks, Eric Nisley, for your questions.
Always Eric. No.
It's always, we know Eric, so it's always Eric leaving really, really good questions for us. So first one, and this was a question that was here, but tell us the difference between an asteroid, a comet, meteor, meteorite.
Yeah, good question. So I probably went too fast. So if you think about, so an asteroids and comets are rock, basically combinations of rock and ice. Comets are further from the sun, from the more outer reaches of the solar system. They're more icy bodies. So they may have like a rocky nucleus, but they're really icy bodies, not as much rock. The closer in to the solar system, you get rock, you get metal, and so the asteroids are more rocky bodies closer to Earth. So the difference between a meteor, a meteorite, not a meteor, wrong. We're not going to talk about those. Those are the rocks people email or tell me about that they found in their driveway.
Yeah.
So a meteor. So when you have an asteroid impact, what happens is you get a piece of that parent body asteroid comes crashing through the atmosphere. It always explodes before it hits, and that's because of a pressure difference as it's slamming into the atmosphere. So when it hits the atmosphere, it's like hitting a brick wall because it's going so fast. And so it explodes before it hits, but as it's coming through, it burns up because of the friction of coming through the atmosphere. That light ball is the meteor. So when you see a meteor shower, the Perseids you were talking about earlier, those are the pieces of coming through the light, the pieces of light, the rock coming through that makes the light that you see. As soon as it hits the ground and you pick it up, you have a meteorite. We have in the museum. Those are meteorites, and so any bit of an asteroid is a meteorite. And we don't have any meteorites we think are from comets yet, so maybe in the future. But I hope answers that question.
Yeah, definitely, absolutely.
Okay.
That was perfect. Okay, and you talked about water on Earth coming from outside of the planet. It was delivered.
Possibly.
Is that where water in other places from the solar system would have come from too, like some of these moons of Jupiter and/or
Oh,
Saturn that
So
have?
that's a good question. So
liquid on them?
water is plentiful out in space. There's a lot of water, and we're talking about, when you talk about water like under the surface, like on Europa or Ceres now in the news of the asteroid with a possible ocean, and Enceladus. These are under the surface. It probably formed with that water. Where that water originally came from, like as these moons were forming or as the planets were forming, it's possible impacts from these icy water-rich bodies out in the outer solar system could have contributed to that. We don't know that. What Earth has is surface water. Earth, in fact, is really considered like a desert. It has only about 0.6% by mass of water, even though 75% is covered. So if, for example, if Europa has the ocean we think it has much more water than we do on Earth, even though it's a small moon. And so Earth does not actually have a lot of water. We don't know. It's possible that Earth's water came from within the planet, from inside, in the rocks, but it seems more likely, and a lot of models suggest that you don't need that many impacts from comets to deliver water to Earth. And it could have lost its water periodically and gotten it again. So we don't have the answers to how all these planets got their water, but certainly water could come from within the planet. The rocks have water in them when they form. A lot of the meteorites we have, they have particles, evidence for water in them. And so it's all a big mix, but everything in our solar system formed from the same big pot of material. So we all came from the same rock, water, dust, and it just sort of spread out in the solar system depending on how far from the sun these objects are. So icy bodies can survive the sun. They don't get melted away when they're far, far away. So,
All right.
yeah.
All right, I'm going to go over here to the chat now. Here we go.
All right.
First one from Eric. Could we make Kool-Aid with water from Mars?
Eric.
We-
I answered Eric's question last time when he asked me about pizza delivery.
Oh,
I
that's
remember that
right.
question, and my answer is the
Back in
same,
April.
is that by the time we send Eric on a solo voyage to Mars, we will 3D print his Kool-Aid. There's your answer. But I
There you
actually
go.
think that, to be in all honesty, we will get to the point of having to create, make our own stuff on Mars if we really want to set up, something sustainable on the planet. So 3D printing of food, as I said before in Eric's last wonderful question, thank you, Eric, was I think the 3D printing of food is really going to become a way to feed colonies in space. And so Kool-Aid, pizza. He's getting his whole, next time he'll ask me about dessert.
Okay, there was great conversation happening here about Jupiter.
Oh,
So first one, is Jupiter all gas because it is so hot?
hot?
Hot.
No, Jupiter's not that hot. It's farther from the sun. It's all gas. It's so big that it can hold on to hydrogen and helium because of its gravity. So most of Jupiter is hydrogen and helium, a big ball of gas. And it is likely it has a core as well, a solid core, and that's being studied still. But Jupiter is so massive that it can hold on to the hydrogen and helium, which are very, very light particles that are very hard for small planets like ours to hold on to. Jupiter can suck up remember, it's a vacuum cleaner, and it mops. It's great. It dusts. No, anyway, but it pulls in all of these light molecules and creates this big, giant ball. And so that Jupiter, because of its gravity, that's why it's such a big ball of gas.
So then the next one, if Jupiter is a gas planet, how did it keep the scars of the comet of Shoemaker leaving?
I'm pretty sure they disappeared in a few months. That's what I understand, is the scars are not still there. If they are, they're very faint, but they would have fallen through the atmosphere. So the scars are more like chemicals that were released with the impact into the gas, so like ammonia, for example. And those were called, I think, I wouldn't think of it as a scar the way we think of, like, it's not like a car ran into a house or something. It's like, this is still a gas giant, but did create a visible, it's mostly like a fingerprint of the impact, and then that went away after.
So it's more like the comet entering Jupiter's atmosphere and gases.
Just like we get meteor impacts, it smashes in.
Okay.
Yeah, just like, so it's like hitting a wall, and then it was pulled apart. Jupiter had already captured it. So Jupiter being so big, it had captured this comet, and then as it neared Jupiter, it was pulled apart because of Jupiter's gravity. So, Yeah.
Okay, for whatever reason, I would tend to think of Jupiter like something like that. Yes, it's giant, it has the gravity, and it pulls things in, but it's gas.
Right.
So
It's
like
hard
throwing
to,
a rock through the air on Earth.
yeah.
But
It's
that's
a little,
not it.
right, it's hard to imagine, and you wouldn't want to go to Jupiter because you'd fall through the surface, the atmosphere. There's nowhere to land. But Jupiter is still pretty fascinating for all the reasons. And it's possible even, there's some ideas that maybe there's microbial life within a certain region of the atmosphere where the temperatures could be conducive. But that's not at all, that's just a theory. Not even.
All right. Is OpenSpace free for Mac?
Yes, it's free for Mac.
It's free for everyone.
It's free for everyone in the entire universe. Yes, and so OpenSpaceProject.com, if you go to it, there's a Windows version. I think the Mac version is still on there. The latest version is right now operable on Windows, and then it's catching up for the Mac platform. But it is free. You download it. It is a beta. It's still in beta. It's still a project. We're still a team working to, there are programmers and there's coders and programmers and all sorts of people involved. And so it's not, necessarily, it's not going to be perhaps as you think of a packaged gaming. It's not like a packaged game. It's a little bit, you play around with it with the menus, and it's a lot of fun. It's just maybe you might think of, people might expect it to be slightly more user friendly, but I think it's really awesome. So I strongly recommend it.
Yeah, it's a lot of fun because I've downloaded it.
Yeah.
And played with OpenSpace, and
yeah,
it's incredibly robust, but not difficult to use.
It's not difficult to use. It's not.
After
it
messing
really
around
isn't.
with it.
And you get, as soon as you figure out the menus, and it really is a lot of fun. I don't, it's one project of many, and I really feel like I can drive around now pretty easily, and I enjoy it. So.
All right. Julian wants to know, how different would Mars look when it had water, and would it look like Earth?
Yeah, that's a great question. We don't know. Mars could have been covered, well, it would have had a different layout than Earth. We think actually the whole northern hemisphere could have been covered with a big ocean. There's the evidence for that is similar to the data set I was showing here with the elevation, is that they can see it's much lower elevation in the northern hemisphere, and that's possible then that it held a whole ocean. Yeah, so we don't know what it could have looked like, but certainly it would have been, it definitely had water in the past. I think we can safely say that. How long it had water, we don't know. It lost its atmosphere, and so it lost its water. And yeah, it could have, we don't have any evidence that it had plants or any other types of life, but that's kind of, that's part of the reason we're going to try to see if we find fossils or something.
Next question. How do our space vehicles and satellites avoid being hit by asteroids or meteors?
Right, well, that's a good question. I mean, sometimes they do, and micrometeorites, especially, they can hit the space station. That's happened, but again, they're far apart. So it's not zero risk, but it's not as risky as we might imagine. They are millions of miles apart, but certainly it can happen. And there was a recent, I remember a few years ago, it was actually a micrometeorite that hit the space station, but they weren't sure if it wasn't an astronaut who drilled a little hole, but they found out it was a meteorite instead. So it does happen. Good it wasn't the astronaut.
Yeah.
That was a good conclusion.
All right. Let's do Glenn's question.
Yeah.
Glenn read this week about Ceres, now believed to have water. You mentioned it too just a minute ago. Should we send a spacecraft there?
Well, people who study Ceres would say absolutely. I mean, everyone's fighting for their space body to go to. So absolutely, any body with water is interesting for astrobiology. But there are many contenders for this. So I would say if we can send a spacecraft to Ceres, we should. We certainly want to go back to Enceladus, which is the moon of Saturn, with water coming out of the surface. There's now a mission going to Europa with the big global ocean. So there are many, perhaps more interesting for life, because Ceres is small, doesn't really have an atmosphere, and so for studying life, you probably want to prioritize larger bodies than an asteroid. But absolutely, I mean, it's always better to go back and study more.
Matthew wants to know, what would it take to prove that life existed on Mars? What evidence
You'd find
would make it definitive?
You'd have to find something that is definitively not from Earth, contaminated from Earth. So that's the first thing, is if you find like a microbe, how do you know it didn't come from a rover? Because it's not zero sterility. There's a minimum level of sterility when we send rovers to Mars. And that's getting better, but there's a limit. So you have to, if we find something that looks like life, that is an organism that's definitely not something that could come from rocks or whatever, the first thing you have to do is prove that it's not contamination from the searching of it, the searching for the life. And then if you do find life, you'd want to then know if it originated from if it's very similar to Earth life, or if it came from a separate origin. And so there are lots of really amazing questions. But if we found life on another planet, I mean, I think it's really, I think a great message is that if we found life on another planet that wasn't from Earth, we would know that we're not alone in the universe. That then we can say life is plentiful because we are just two tiny little planets amongst billions of planets. And so then we can say we're likely not alone. And then you ask other questions, but yeah.
So if people want to learn more about OpenSpace, they should visit
OpenSpaceProject.com.
There you go. And I think the folks from OpenSpace have been dropping the link in the chat. So if you want access to it, do that. I'm going to go ahead and let everybody know, while I've still got you, that I'm going to drop a link to a survey about tonight's OpenSpace program in the chat as well. In fact, I'm going to click enter on that right now. There it is, a link to a survey about tonight's show using OpenSpace from the folks who are helping to develop OpenSpace. So if you've got 5 minutes after the show, visit the link and give them your feedback. It'll greatly help us, help the OpenSpace collaborators, and we want to make sure you're getting a good product.
Yeah, absolutely. Yes, please fill it out.
So everybody, I'm going to do one last look here. The folks from OpenSpace answered the ones that were here. I'll go ahead and verbalize them, though. Lucas was asking, will OpenSpace be getting data from OSIRIS-REx?
Yes. In fact, there is what I didn't explain is that when you start OpenSpace, there are scenes you can choose. And one of the scenes is OSIRIS-REx. That is actually more about the spacecraft now. But as more data sets come in, I mean, I didn't have time to go into all of it, but basically all the data comes from NASA, a NASA portal that packages the data and then has to be put into the code. And so some of the data, like from Earth, come from servers that regularly image Earth, but other data, like from missions, has to be imported into OpenSpace. And so it's not a simple thing. And so as data comes, OSIRIS-REx is sample return. So my thought is that we will get imagery of the asteroid, really good imagery, and have that eventually, hopefully, in OpenSpace. It depends a lot about, I'm sure the data guys or the programmers will answer more about this, but it also depends on how the data are packaged and how much has to be manipulated to get the data into OpenSpace. So it's a complicated set of codes.
Yeah, so they said we have OSIRIS-REx and Bennu
that's the
in OpenSpace, but maybe you're asking about the sample return. No plans for that just yet.
Yeah, Bennu, but right. I think maybe, but I will say once we get the imagery of Bennu, like really high resolution, that might be something that people would be interested in. But again, it depends on how the data come through from the mission and if they can be put into the software. Yeah.
All right, I did miss one last question here from Eric. What's your favorite science fiction movie that takes place in space?
2001: A Space Odyssey. Absolutely.
There you go.
Yeah.
All right. Hey, let us know yours in the chat and in the comments. As for us, I think we'll call it a show. Thanks, everybody, for tuning in.
Thanks, everyone.
Thank you, Rachel, for coming out to the museum to put on the show for us. I'll let everybody know we host the Science Cafe every Thursday night right here on our YouTube and social media channels. So you can like, click follow, subscribe, click the bell to get notified on YouTube. That way, every Thursday at 7 p.m. Eastern, you can join us right here on the internet for more great and exciting speakers. Next week, we're going to be doing a panel discussion, actually, with some museum staff and book editors who put together a guide to outdoor experiences in North Carolina. We're going to be learning about science and nature through exploration. So don't miss that. You want to join us right here, 7 o'clock. Click the bell, like, subscribe, all that stuff. Oh, follow the Museum of Natural Sciences, too, on social media. We're at Natural Sciences on Facebook, Twitter, and Instagram. Great stuff all the time. And if you're just looking for something to do, we have live events several times a week, every week. naturalsciences.org is your link to figure out what's going on and what you can participate in. Thanks, everybody, for tuning in. I hope we'll see you again real soon here on the internet and maybe one day soon here in downtown Raleigh at the Museum of Natural Sciences. Bye, everybody.
Bye.